Welcome back to day 2, part 2. Um, so this next example is kind of 2 parts. So they give us a picture here, which is convenient. We don't have to worry too much about finding limits. This is more about the concepts here. In the last one we saw, we rotated around the line y equals -3. Now we're rotating it around a positive line, which is y equals 12. This bottom here, this curve is 9 minus x squared. This is the line y equals 12, and then x equals 3 tells us where to cut off the region. Should really say and x equals 0. It's just the piece of this in the first quadrant, but this is the region we're talking about. So we're going to try and, like, again, I want you guys to kind of really get your heads around the idea that these kind of all have the same formula. I'm going to keep writing it so that you get the idea that we're using the same formula over and over again. Pi times the integral from a to b of big R squared minus little r squared. We're going to find these vertical distances by doing top minus bottom. Now, it doesn't matter whether the thing on top is the straight line or the thing on top is the curve. It's just which one's on top, which one's on the bottom. So big R of x here. So this is the thing. So this is big R right here. Right, it's a distance from the outer edge to the axis of rotation. So it's top minus bottom. So it's 12. This is y equals 12 minus f of x, which is 9 minus x squared. So 12 minus 9 plus x squared. If I do the subtracting, the distributing of the subtracting in my head, and I get 3 plus x squared. And little r of x, well, little r of x is like, there actually isn't one here because the edge of this region here is the line y equals 12, and the axis of rotation is the line y equals 12. Like, the fact that this is the edge and it is the axis of rotation means that there is no little r. Little r is 0 or something. There's like, I don't have to sweat it for this one. What that means is that the cross sections of this thing should be disks, and you can see from this picture that the cross sections are disks. And I can't emphasize this enough. That happens when the edge of the region, y equals 12, is the same as the axis of rotation. Rotating at about y equals 12, the edge is y equals 12. That means that there is no inner radius. So the volume here is pi times the integral from 0 to 3. It tells me it's x equals 3 of big R squared minus little r squared, which is really just going to be big R squared for this one. Because little r squared, little r is 0, so little r squared is 0. So if I square that, I get 9 plus 6x squared plus x to the 4th dx. And now I do my integration. 9x plus 2x cubed plus x to the 5th over 5 from 3 to 0, which is pi times 27 plus 27 times 2 is 54, and then 243 over 5. And you could add these together in your calculator and get a number, or you can just leave it like this, either way. The point of this problem is not so much, do you know how to add fractions to whole numbers, but do you know that when the edge of the region, i.e. y equals 12, and the axis of rotation, also y equals 12, are the same, then you get these disks and not washers, and your little r becomes 0, and this thing reduces to just pi times the integral of r of x squared. Now we're going to do the same thing, but we're going to spin it around the line y equals 15. That's what this is. So now you can see from the picture, these are going to be washers. There's like an inner radius now, and that's going to be the little r of x. So here's the region, and here's the axis of rotation. So now big R looks like this. It goes from the axis to the outer curve. Big R of x is going to be top minus bottom. The top is 15. The bottom is f of x, which is 9 minus x squared. So I do 15 minus 9 plus x squared which is 3. Oh, that's 6. That's true. 6 plus x squared. And little r of x is right here, right? From the axis of rotation to the inside radius. And in this case, little r of x, top minus bottom is y equals 15 minus y equals 12. It's 3. And it's like always 3. And you can see from the picture, and you can kind of maybe guess here, that like this radius here never changes. It's always just 3, and that means that the inside part is like a cylinder. It's like a little cylinder that gets chopped out of that. That's fine. That's little r of x. We still have to include it because this is not a disc, it's a washer. There's a hole in it. So I can do my volume thing. Still going from 0 to 3. I'm going to do big R squared minus little r squared dx. And I'll do a little math here. If I square this thing, I get 36 plus 12x squared plus x to the 4th minus 9 dx, which is really the integral pi times the integral from 0 to 3. 36 minus 9 is 27 plus 12x squared plus x to the 4th dx. Now I do some integration because that's what calculus is about. 27x plus 4x cubed plus x to the 5th over 5, evaluated from 3 to 0. Let's see, we get 3 times 27 is 81. 3 cubed is 27 times 4 is 108. That's right. Minus 243 over 5. That number seems to come up a lot in these problems. Minus, they're all zeros when you plug in a 0. So this is the answer, 189 minus 243 over 5, which is some number that I'm not going to figure out right now, but this is the answer. So you can see from all the examples we did, this one, like the top was like a curve, quote unquote. It's not a horizontal line, and the bottom was also a curve, but it's still top minus bottom. Like there's still big R squared minus little r squared. We find the r's by doing top minus bottom. And this one, it was 2 curves, but that's okay. Here's the axis of rotation. Big R is the distance from the curve to the axis. Little r is the distance from the inner curve. Let me say that again. Big R is the distance from the outer curve, meaning the one that's farther away from the axis, minus the axis. Little r, I said that wrong. Little r is the distance from the curve that's closer to the axis of rotation. And we find those by doing top minus bottom. And in this case, it was 2 curves and a line that was not y equals 0. That's fine. You just do the same thing. You just subtract top minus bottom. This time we had, this was different in the sense that the axis of rotation was like above the quote unquote above, higher than the curve, but that's fine. You just do top minus bottom. You do the axis of rotation now. It's a number, this time it was 12 minus this thing. And in this case, the edge of the region y equals 12 was the same as the axis of rotation. So you end up with just 0 for the inner radius. That means we're talking about disks here. And then this was the last example where we had now like the distance between the inner radius happened to be constant here. It was 3 the whole time. And so that just becomes 3, it becomes 9 in here, it becomes just part of the problem. So that's how these work. We'll do some examples at some point probably where you revolve around the y-axis. That's the only thing really left we haven't done yet. And that's pretty much the same procedure, except instead of doing top minus bottom, we're going to be doing like right minus left to find distances. But to my way of thinking, that's kind of day 3 of this. So we'll see how that goes. But that's it. Hope you enjoyed. Bye.